So I would like to now, seriously, for me, it's a really huge honor to give the floor to the CEO of the most important semiconductor research technology center in the world. Ladies and gentlemen, the CEO of Imec, Luc van der Hoven.
Welcome to this session, where we're honored to introduce Luc van den Hove, the President and CEO of Imec, a world-leading research organization with headquarters in Leuven, Belgium. With over 5,500 employees and operations across multiple continents, their cutting-edge research is advancing crucial technologies for next-generation communication systems, healthcare innovations, and sustainable environmental solutions. Imec plans to expand its global presence with the recent signing of an MOU with the Spanish government and the region of Andalusia, with the intention to establish a new 300mm R&D process line for specialized chip technologies in Malaga. This will further strengthen its role as a key player in the global technology landscape. Luc van den Hove has been a pivotal force behind Imec's remarkable growth and influence. Under his leadership, Imec has consistently pushed the boundaries of what's possible, establishing itself as a critical partner for industry giants. Please welcome our keynote speaker.
Okay, I would like to thank the organizers for making such an impressive introduction video. And I would also like to thank the organizers for inviting me to give this keynote at this impressive forum. This year marks the 40th anniversary of Imec, and I want to begin by taking a trip down memory lane, going like 40 years back. Some of you might find it hard to believe, but this was cutting-edge technology at that time. Tape recorders, videotapes, floppy disks. Well, what a change we have seen in those 40 years. Today, young people even rarely make phone calls. They chat, use Insta, TikTok, all on a small device that has the most sophisticated cameras with powerful embedded AI for image recognition and even simultaneous translation. We all have a supercomputer in our pocket now. The world has changed in 40 years in ways we could not have imagined. The explosion of technology applications that we have seen over the last few decades has caused a revolution. And this, combined with the AI revolution that we have seen over the last 2 years, I mean, this is truly phenomenal. We can fairly refer to it as a Big Bang. And it's all the direct result of Moore's law. With every step of miniaturization, more complex devices can be made. With every step of technology, more powerful applications become possible. Last year was the year of generative AI. With the introduction of large language models, such as ChatGPT, artificial intelligence has suddenly become accessible at everyone's fingertips. But initially, AI was off to a much more difficult start. It's only through the recent availability of massive compute power, to a large extent enabled through Moore's law, that the AI burst actually could happen last year. The compute needs for AI have been exploding, and recently, model complexity grew at a rate of more than 2 times every 6 months. In fact, faster than Moore's law. And this led to a massive expansion of compute capacity in data centers. However, just expanding those data centers in an exponential way is obviously not sustainable, as their energy usage would also explode in an exponential way, eventually requiring more power than what is available on Earth. So we need more energy efficient, more performant compute platforms. And this has been realized by the transition from classical CPUs towards GPUs, GPU architectures that leverage massive parallelization. Now, orders of magnitude compute efficiency have been realized by this move from CPU to GPU. And this in combination with, of course, drastically increasing the number of transistors per compute unit, reaching up to even 200 billion in the most recent examples. This has been achieved by using the most advanced technology nodes, and this in a chiplet configuration. But we're here today to talk about what is next. Only a continuation of Moore's law, we believe, and this in combination with new architectures, architectures even beyond GPU, will allow energy-efficient implementation of this exponential increase in the required compute power. But also, the AI models will evolve. The recent revolution in AI has been realized by using transformer neural engines to train these large language models. But if you want to evolve closer towards true intelligence, a combination of multiple models may be needed, each serving a specific purpose and interacting with each other. An AI system that can combine large language models, perception models, and actional models, gradually evolving to some form of reasoning. Whereas the GPU architecture may be ideal to implement large language models, to implement this next vision, we may need a broader variety of alternative compute architectures, each optimized for their specific AI workloads. This will actually drive a need for more versatile chip architectures and technology platforms, such as 3D, but also silicon photonics. A one-size-fits-all approach may not be optimal. Now, one way to combine these multiple chip platforms is through chiplet integration. The progress in 3D heterogeneous integration now allows for extremely high bandwidth interconnections between those multiple chiplets, nearly similar as if everything was integrated on a single chip. This allows the build-out of these massive compute systems, much bigger than what would be possible on a single chip. Now, whereas the HBM memories are nowadays configured as a 3D stack of DRAM chips, each of the processors is typically fabricated as a single monolithic chip. As the next wave of 3D integration, we have proposed several years ago to further disaggregate these systems on a chip into multiple layers, stacked using advanced hybrid bonding and true silicon via technologies. By splitting up the chip in different layers, each layer with its specific functionality, we can now optimize the process technology for each part of the chip. It actually allows one to also bring the memory much closer to the logic circuitry, which is very important for many AI applications. We could even consider to split up the logic layer into two layers, into multiple layers. One in which we optimize the transistor for density, another one where we optimize for drive current. This will allow us to scale the dense transistors much further than when the transistors need to be optimized for all requirements simultaneously. We refer to this approach as CMOS 2.0, a platform to further extend the scaling roadmap beyond what we currently assume possible. On this slide, we present our latest view on how we believe this roadmap can be further extended for many more generations during the following at least 2 decades, we believe. Whereas gate-all-around transistors, these nanosheet devices, will be standard as from the 2-nanometer generations, probably lasting for 3 more subsequent generations. A few years ago, we presented the CFET device, a complementary FET device, as the next possible device architecture. CFET is an extension of this nanosheet concept whereby we're stacking NMP transistors on top of each other. And by stacking these transistors, we're obviously realizing a significant scaling effect beyond litho-based scaling. However, by stacking those transistors, it becomes increasingly difficult to reach out to all the terminals of these transistors. We will need a rather complicated local interconnect structure. To leverage this density advantage that we obtain by stacking, we will need dense interconnects not only on the front side, but also on the back side of the wafers. This cross-section shows a TEM of the devices that we have recently demonstrated, fully functional CFET devices with backside interconnects. We're in this way, in fact, extending our roadmap by introducing a backside interconnect roadmap based on advanced wafer bonding with ever more stringent bonding requirements. Now, to realize terabit scale connectivity, silicon photonics clearly have emerged as a promising solution. By leveraging the mature and high-volume manufacturing processes of the semiconductor industry, silicon photonics offers high bandwidth, low power consumption, and low latency in a cost-effective manner. For several decades, we at Imec have been developing our silicon-integrated photonics platform, thereby leveraging massive CMOS integration knowledge. We are continuously fueling this platform with new advanced features. This platform is available for industry for prototyping and low-volume production. We have a clear roadmap to further develop optical networking to meet the requirements of AI and HPC systems. Our state-of-the-art silicon photonics enables 800 gigabit per second and first generation 1.6 terabit per second pluggable optics. Looking ahead, we're working on hybridized photonics, silicon photonics platforms. These platforms will push the boundaries, supporting pluggable optics up to 3.2 terabits per second connectivity. And wafer-level co-packaged optics aim to achieve further 100x scaling in optical interconnect performance. Wafer-level optical interconnects are likely to replace long-range copper interconnects by leveraging 3D-enabled silicon photonics. Now, how the future will look like exactly is obviously hard to predict. But what we do know is that the advances in these technologies and systems will kind of touch every corner of society, way beyond what we can imagine today. The automotive industry, for example, is undergoing one of its biggest transformations ever. To achieve the EU goal to reduce road fatalities to near zero by 2050, significant advancements in vehicle safety, particularly through advanced driving assistance systems, will be required. Advanced systems that can kind of mitigate human driving errors. Now, next to camera sensors and radar systems, LIDAR scanners are indispensable for smart cars to build an accurate, real-time picture of their surroundings. However, mechanical LIDAR sensors with rotating elements are too bulky and far too expensive. Integrated photonics will be indispensable to make them affordable and with appropriate form factor. The ideal solution is to integrate all the LIDAR components on a single chip, including an optical phase array with automatic calibration and antennas to accomplish the beam steering through controlled phase modulation without any moving parts, containing an integrated, custom-designed 3.5 laser source. A novel 2D detector array achieves coherent detection, and on-chip electronics can manage the calibration and signal conditioning detection and processing. An ambitious concept for which we are developing the enabling technologies and photonic electronic building blocks in collaboration with our Dutch colleagues in the Photon Delta program. To process the huge amounts of data coming from all these sensors, massive in-car compute capabilities will be needed. Last year, we have launched our Automotive chiplet program. Within this program, we're developing the concepts for future super complex electronic control units to be configured in a flexible way, hence based on chiplets. We're doing this by bringing together the key players from the entire automotive ecosystem, including leading car manufacturers, tier 1 and tier 2 players, and chip and EDA providers. Microchips, integrated photonics, and AI are also transforming the healthcare industry, accelerating complex diagnosis, optimizing the efficacy of drug testing, and providing the building blocks that are required to enable personalized therapies. We have witnessed the genomic revolution. As a matter of fact, many of the leading sequencing companies have partnered with us to build their next generation sequencing chip with higher throughput and higher sensitivity using our technology platforms building on our photonics capability. Now, sequencing the protein actually is the next big frontier. However, analyzing a proteome is vastly more complex than DNA sequencing. To make proteomics accessible in clinical practice, we need scalable implementations for detecting, quantifying, and sequencing these proteins. We can achieve this by using highly parallelized protein sensing arrays that provide single molecule resolution. This involves CMOS image sensors with readout and actuation electronics. This combined with photonics for distributing, modulating, and amplifying the light across these chips. And this in combination with sophisticated microfluidics. All of this is being developed in our 300mm facility. Another emerging application domain in health where we see photonics playing a crucial role is biosensing. Accenture, an Imec spin-off, is commercializing our Raman-on-chip technology for rapid therapeutic drug monitoring. The Raman-on-chip is built using our silicon nitride waveguide process module. Photonics has the potential to clearly revolutionize AR and VR technology by enhancing display resolutions and reducing the need for cumbersome headsets. Swave, another Imec spin-off, is developing realistic holographic projections using advanced sub-wavelength diffractive optics and phase change materials to achieve high pixel resolution. This enables true realistic vision holograms without AR, VR headsets. Another application domain where photonics can be key enabler is clearly quantum computing. We're leveraging a silicon nitride platform to develop scalable and fault-tolerant photonics chips in collaboration with several startups, including Xanadu. Now, the awareness of the strategic importance of chips to enable all of this has increased enormously, especially, as Maria mentioned before, during the aftermath of the COVID pandemic, and it has been amplified by the ongoing geopolitical unrest. As a result, as was mentioned, multiple CHIPS Acts have emerged. And if those are implemented in the right way, we believe that these CHIPS Acts will be very instrumental, not only to ensure a more resilient microchip supply chain, but also to further tackle the phenomenal innovation challenges. However, the various CHIPS Acts need to be done right. They need to result in an acceleration of the innovation process. Each region clearly has its strength. Also, Maria mentioned this. However, if the CHIPS Acts would be set up such that each region would try to do it all, try to become fully self-sufficient, we strongly believe that it would result in a major setback. To make real progress, the fastest possible progress, we need to rally the experts from all over the world. We should avoid duplication. As the R&D challenges are unprecedented, to tackle these effectively, we need critical mass, and we need to combine the best of the best through global collaboration. And that's what we're doing in Europe. By setting up these pilot lines, and these are the 3 first that are being set up, by setting up these pilot lines in a complementary way, each focusing on our strength, not duplicating, but collaborating. And I'm excited that Imec has been selected to act as the primary R&D pilot line for the most advanced technology nodes as part of the EU CHIPS Act, and has been awarded with a major project that will allow us to expand our pilot line infrastructure. We'll add more than 6,000 square meters of clean room and more than 100 of the most advanced tools. And this amounts to an investment of more than 2.5 billion euro. This animation shows a detailed layout of the first phase of this facility expansion. The first series of tools will be installed in a next module in the expanded shell of our current 300mm fab. In this expansion, we will install more than 100 of the newest tools, including ASML's full suite of advanced lithography and metrology equipment, including the next generation 5200 high-NA scanner. We will then connect this module with the next fab, our Fab 4, which we will start building. This will be another 4,000 square meters. And this is currently being designed, and we will start the construction during next year. This major expansion will allow us to double our capacity and to install all advanced technology capability that we will need for the next 5 to 10 years. We will make these complementary capabilities in these pilot lines available to a large number of competence centers spread across Europe, focusing on chip design, design enablement, and skill development. But as was mentioned, we also signed a memorandum of understanding with the Spanish government and the region of Andalusia with the intention to establish an additional 300mm process facility where we will concentrate our work on specialized chip technologies, and this here in Malaga. The goal is to extend our R&D capabilities with a facility here in Spain focused on processes and materials to boost innovation in upcoming domains such as health and augmented and virtual reality. But we have to extend this model to a worldwide level. Our industry is global. It is one global ecosystem. Therefore, also the R&D needs to be reorganized on a global level. We should not decouple the continents. As we're doing here in Europe, we make sure that we need to connect the strengths. We have to tackle these huge challenges in the most effective way. I'm convinced that setting up a strategic partnership between these various chips acts, avoiding duplication and leveraging collaboration will be absolutely essential to effectively support our global industry. Now, on the people dimension, the success of those various CHIPS Act initiatives, but also the success of the growth of our industry in general, will depend on our joint ability to attract and develop sufficient talent. Estimation of projected talent gaps are really enormous. It is clear that growing the pipeline, the talent pipeline, is a very important priority. We're facing challenges in many aspects of our education system related to content, infrastructure, and format. We're therefore rolling out a comprehensive talent development program targeted to all layers of education from primary, secondary school, over higher education to lifelong learning. A better match between curricula and the needs of industry will actually be crucial. And this is where we can play a role, obviously in strong partnership with our university and high school partners, also here in Spain and in Malaga. Because indeed, the opportunities for our sector are clearly endless. The swift integration of microchips, photonics, and AI into every aspect of our life is truly remarkable. And we at Imec are putting everything in place, our partner network, our infrastructure, and our amazing people to contribute to enabling the roadmaps to build this future technology, starting from a rich legacy, our 40 years of history, but above all, with a promising future in sight. And that future starts here, and it will be one to love. Thank you.
Thank you very much, Luc van der Hove, for being with us today. I know many of you have questions. He will be a panelist later today next to the CEO of TNO. Doesn't get any bigger than that, and interviewed by the Jim Kafka, president-elect of Optica. That will happen later today.